This example has two parts to it, but we're actually only really going to need to do one big computation. In the first part, we're going to find a scalar equation for the plane tangent to the surface described by z equal to f of x and y equal to square root x squared plus y squared plus 1, when x and y are equal to 2. And then in the second part, we're going to construct the linearization of f of x and y when x and y are both equal to 2. And we're going to use this linearization to approximate f when x and y are both equal to 2.1. So let's start off by finding this scalar equation. We actually did a bunch of work in the notes to say that the scalar equation for the plane tangent to a surface is given by the function evaluated at those points plus the partial derivative with respect to x evaluated at those x and y values times x minus a plus the partial derivative with respect to y of f evaluated at those x and y values times y minus b. So to get this scalar equation, we really just need to evaluate the function at 2 and 2, the partial derivative with respect to x at 2 and 2, and the partial derivative with respect to y at 2 and 2. Given the symmetry between x and y in this problem, and that we're using 2 for both x and y, we're really only going to need to do these calculations once for the partial derivatives. Let's start off by finding f at 2 and 2. Well, that's just equal to 2 squared plus 2 squared plus 1, all square rooted. So that's square root of 9, or 3. Now let's find the partial derivatives. So partial derivative with respect to x, this is equal to the partial derivative of square root x squared plus y squared plus 1. And we'll treat y like a constant here because we're taking the partial derivative with respect to x. And this will give us 1/2 1 over the square root times 2x. It all just simplifies to give us x over square root x squared plus y squared plus 1. When we evaluate this at x and y both equal to 2, we'll get the partial derivative with respect to x at 2 and 2 is equal to 2 over square root of 9 again, which just gives us 3. So that's 2/3. By symmetry, between x and y, we'll just get y over the square root x squared plus y squared plus 1 for the partial derivative with respect to y, and that's going to give us the exact same value for the partial derivative with respect to y, evaluated at x and y are equal to 2, so just 2/3. So now we can write down the scalar equation for the plane. It's just going to be equal to 3 plus 2/3 x minus 2 plus 2/3 y minus 2. So that's all we have to do for part A. This is the scalar equation for the tangent plane to the surface above the points x and y equal to 2. For part B, we're asked to use the linearization of f of x and y at x and y equal to 2 and 2 to approximate the function at 2.1 and 2.1. Now remember from the notes, the linearization of a function is just given by the equation for its tangent plane constructed at that point. So the linearization at 2 and 2 is just going to be equal to 3 plus 2/3 x minus 2 plus 2/3 y minus 2, the exact same equation. And we can use this to approximate our function near that point. Since 2.1 is close to 2 and 2, we have that our function should be roughly equal to our linearization evaluated at these points. And we can just work that out by hand. We'll get 3 plus 2/3, and then 2.1 minus 2 plus 2/3, 2.1 minus 2. That's 3 plus, I've got 2 of these terms, so I'm just going to write it as 4/3. And then I'll get 0.1, I'm going to write that as 1/10, so I don't have any decimals floating around. And then I can rewrite this as 90 over 30 plus 4 over 30 to get an exact result of 94 over 30. How does this compare to the actual value of the function? Well, we'd have to plug this into our calculator, but f at 2.1, 2.1 is equal to the square root of 2.1 squared plus 2.1 squared plus 1. And if we plug that into our calculator, we get approximately 3.1337. Our result, 94 over 30, to figure out what that is in decimal form, we could plug it into our calculator, and we'd find that this is equal to 3.13 repeating. I'll just round it off after 3 3s for comparison. So our linearization actually gives us a really good approximation comparing these two numbers. And it actually makes sense as well that we're getting an under approximation, because if you were to sketch this surface, you'd find that it's the upper half of a hyperboloid of two sheets. So if we put x and y here, then we're basically getting some point here on our surface, and if we construct a tangent plane there, that tangent plane sits below the surface. So everywhere near that point, if we use the tangent plane or the linearization to approximate the values of that surface, we're going to get underestimates. All right, that's all I wanted to say about this for now. Thanks.